Revolve command is quite simple in terms of the sequence of steps that you must make in order to create the desired result. But we are interested in analyzing this kind of operation from the topological point of view. So, as I'm not working in the origin of my coordinate system, the more efficient way to create a revolve is now create a vertical line in order to use it as a revolve axis. And what I'm going to do, I'm going to create also a vertical rectangle. This is something that eventually you might take as a reference for creating complex shapes in a particular orientation in space without having to change eventually the coordinate planes with any of these comments here. So now that I have this frame here as a reference, I can create a NURBS curve. Like, for example, starting from here, and then I'm going to use this rectangle as a guide for placing my control points. Okay, so I'm going to place another couple of points here, and then one in this is a degree 1. No, I need a degree 3. Okay, so a couple of points, and then a point in the vertex here, and then another one here, another one here. And then I'm going to place 1, 2, and 3 points. And then I'm going to place here some 1, 2, and 3, and another 1 and 2 here. And then 1, 2, and 3. And then finally 1 and 2. Okay, so I've created this kind of NURBS curve. I'm going to lock this rectangle in order that we can easily select our curve. And I created this kind of 3 points structure because if I move them, I know that I can reach this depth inside the NURBS curve, and also this set of 3 points here in order to do something like this eventually. Okay, not because this is a particular design, but just to remind us of the power that we can access in order to create the right NURBS topology and being able of creating some controlled deformation. Okay. The reason why I placed here, for example, 2 points before the corner point is that if I only take 1 point here, the line would not go back and touch the right side of this rectangle. Okay, because I would only have a tangent information here, but not the tangency, the physical tangency to this side. So I needed 3 points in a row in this point, and also 3 points here. Okay, while in the last step I just need the curve to become perpendicular to the left side of the rectangle. And in this case, for example, also in the bottom section, these 2 points here guarantee that my curve is getting to this endpoint perpendicularly. And this is important because as this profile is going to revolve around this axis, if I don't have an horizontal tangency, or rather a tangent which is perpendicular to this side, then during the revolve, I will get some vertex or discontinuity in these two endpoints. Okay, so once I have created this structure, I can use the revolve command, select the curve to revolve, which is specifically the profile, and then select the revolve axis, which is just 2 points aligned with the axis that I want to use. And then you can decide if you want to create, for example, a full circle, which is a full revolve around this axis. So you want to create some partial revolve, for example, from here to here. Okay. But anyway, it's just the standard use of this command. Now, I'm not going to use anything right now, this function. I'm just using the full circle, so I create this full revolve surface. Okay. Surface because I have used a profile which has no internal discontinuities. Okay, so remember that when you create a NURBS curve with degree 3, you have up to curvature continuity. Okay, so for most of the applications, of the common applications, this means that the curve is internally extremely continuous. Let's say so. Okay. So as this is continuous enough, when you revolve that curve around the axis, you will get one single surface. So if I select this one, you see that Rhino say this is a closed surface. So normally, in order to obtain a volume, a closed volume, you need to create some polysurfaces. Okay, but there are some particular surfaces or solids which are the sphere and the ellipsoid and the torus. They are they are solids made up of one single face or one single surface. Okay, and everything that is the word is homeomorphous with this kind of objects here is also a one single closed surface. So basically, homeomorphism here means that if you take, let's do it like this. If I take a sphere, and you know that the sphere, it's a smooth object, but it's not an organic object. Okay, so it is not organically deformable. Okay, it has a very rigid structure. So if I select a sphere, for example, and activate the control points, you see that I have this extremely rigid set of control points, which is a cube. Okay, and if I try to move any of these points here, I produce a discontinuity along the surface of the sphere. So if I take, for example, this point or any other, right, and move it away, well, no, this I cannot move this because this is the sphere as well as the circle is actually a rational object. Okay, so it has different weight for the points. So in this case, for example, if I take this one, you see that I'm creating this kind of discontinuity. Well, actually, this is more visible if I do something like this. Okay, so you cannot deform. The sphere is not a deformable object, and the same happens with a circle. So if I create a circle, I see this square set of control points. And in this case, consider this as this isocube for the sphere. Whatever point I touch here, I produce this kind of discontinuity along the path on the curve. Okay, so it's an extremely rigid geometry. But I can rebuild this sphere, give the sphere like 8x8 control point, which is well, it is not that important, the amount of control point. The important thing is that I have 3x3 degree and not 2x2. Okay, so if I do this, now I have a deformable sphere. And whatever type of deformation I manage to do with this sphere, I don't know, something like this, will produce a surface, a result, which is a surface, a closed surface as well as the sphere. So homomorphism is something that you get from one volume just by deforming that volume without ripping the surface or cutting the surface. You get to another shape, which in this case is our revolved surface. So it's evident that you can get to this point starting from a sphere, for example. So any object that can be obtained by deforming a sphere is a closed surface, like this one. And of course, you can recognize in this case that you have a pole here, and this internal edge, which is the only internal edge for our solid. By the way, topologically speaking, Rhino surfaces are always rectangular. Okay, so in order to obtain this kind of object or this kind of object here, which is basically the same, what you need to do, you need to take the standard rectangular surface in Rhino, which is basically this one. And then if you imagine, let me take the pencil. Okay, if you imagine that you can take this side here and this, and start to bend this surface like this, in order to have this side coincident with the other one, with the opposite one, then this line is going to become a circle like this, and you will have the first result that you get is a cylinder. Okay, and once you have the cylinder, which is actually is also having this opposite edge here, once you have the cylinder, you can take the circle of the base of the cylinder and contract it into a one single point, which is going to be the pole, and also on the other side. And so the only edge that you have, the only longitudinal edge that you have inside a cylinder is going to bend towards the pole, and you get to a sphere. Okay, so there is always a rectangular topology behind any Rhino surface. Okay, so it means that this kind of object here has some singularity with correspondence to the pole. So it's kind of difficult to eventually use this kind of object for further operation that we are going to discuss today, which are very important and very complex in terms of topological modeling. Okay, so keep in mind that this object has this kind of singularity. Okay, and eventually, I don't know if we are going to use this kind of object, but once you know the process that we are going to study today, then you will also understand what's the problem with this kind of geometry. But anyway, I am just going a little forward with this. So how does this thing work? Well, of course, as this is a singularity, basically what you can see if you try to extract an isocurve is that you have this circular isocurve, because the rule of the revolve surface is basically a circular revolve. It's a rotation of a profile around an axis. So in this direction, you always have circles. Okay. And by the way, as the revolve surface is created automatically, if I extract one isocurve, which means if I extract any isocurve and take a look at the topology of this one, you see that this is exactly a NURBS circle. Okay, where NURBS circle means that this is a degree to NURBS spline, which is actually rational. Okay, and if you want to take a look, for example, at the rational part of this curve, you simply select the control points, like for example all of them, and Rhino says that there are various weights. Okay, and if you want to understand a little more, a little deeper this thing, you see that control point weights vary from 0.707 to 1, which is square root of 2 divided by 2 and 1. So this is the weight of the control point of a circle. Okay, so if I select this one, this point has this value, while if I select this one, this point has this value of the weight. Okay, so this is a rational curve. So it's very complex in terms of in topological terms. But anyway, you see that as the rule of revolved surfaces is the circular rotation, what you get in the horizontal direction of the isocurve is always a perfect circle. Okay, while on the other hand, the isocurve that you get, for example, from the other direction is exactly the same profile that we used at the beginning. So if I extract this isocurve here and move it away and select it, we can recognize exactly the same topology. So and the tangency, 3 points for deforming in this area, 3 points here, and so on. Okay, you see that the surface keeps the initial topology of the profile curve intact and uses the topology of a circle for the other orientation, the other direction of the isocurves. Okay, so if I select this, as this is a closed surface and this one single surface, I can also activate the control point of this object. And what I get is a circular scheme, a circular topological scheme from top, and I get our profile topological aspect from the profile or the front elevation view. Okay, this means that this thing here is deformable in the vertical direction, and it's also deformable in the horizontal plane. But if you do it, you will produce some discontinuities along the surface. So if I take, for example, let me switch to wireframe. If I take this object here and take all these lines of control points and all these lines of control points and do something like this, okay, what I am creating, if I see it with the shaded viewport, you see that I am creating discontinuities in these along these 4 edges of the surface. Okay, and it's interesting because while here we have a discontinuity that corresponds to an edge, which is the only internal edge, here we don't have internal edges. So you see that, and this is also valid for the circle, the standard circle. You see that here we have these control points that lie on the surface, and we saw that when we have control points that lie on the surface, these are most likely kinks or knots with full multiplicity. In this case, if we analyze the knot vector of a circle, these knot values would appear twice inside the knot vector because this curve has degree 2. Okay, so full multiplicity for a degree 2 curve means that the knot value appears twice. Okay, and here in this surface, we saw that we had these isocurves in the quadrants of the surface. And as the horizontal rule is the circle, we also know that these are not simple isocurves, these are kink lines. And as you can see, if I try to deform, I really get some crease along the path. Okay, so this is the effect of a standard revolve execution. Now I'm going to take, and of course, yeah, if I take this, for example, and I select, well, let me get rid of all the rest. Yeah, and I go into the front viewport and take this surface and activate the control points. Okay, so if I want to deform this in the vertical direction, hypothetically speaking, I can do it. I can take these 3 points here and move it like this. Okay, and I'm going to deform the object vertically in a smooth way, because vertically we have the rule of the profile, which is a degree 3 curve with the proper distribution and amount of control points. Problem is that if I don't select the proper set of control points, I might produce some kind of discontinuity or creases along this surface because it is degree 2 in the horizontal direction. Now, what does it mean to select the proper set of control points? I'm going to show you this with a sphere, with a real sphere, actually. So I'm not going to rebuild it this time, and I'm going to activate the control point. Okay. So whatever operation I do on this sphere is going to produce some kind of crease, right? But if I select, for example, in this case, the whole plane of control points here, and I move it, I'm not creating any discontinuity because I'm not working with these points here individually. Okay, so the points that I have here are the kinks, and I cannot touch them. But I can touch the whole plane that contains the kink and keeps the tangency untouched. So remember when we saw the freeform curve like this, and we decided to add a kink to this curve like here. Okay, so we know there is a discontinuity here, but if we don't change the, oh sorry, let me do this in a more visible way. Just give me a second. So let me see where the knots are. Okay, they are here. I'm going to add a kink here, which is a safe area. Okay, so add kink here, like here. Okay, so if I go and take a look at the topology at the control points, you see that yes, we have a kink here, which is this one. But you also see that when a kink is added or is present, there is always, along a continuous smooth curve, there is always a set of 3 control points whose orientation or that are aligned in the same, along the same line. This means that this kink is actually an internal discontinuity, but it's invisible because the tangent to the curve before the kink is equal to the tangent to the curve after the kink. So there is a discontinuity, but it's invisible initially. So you can think about these quadrant points for our sphere as invisible discontinuity. Okay, so this point here is determining the tangent in this direction, and this point is determining the tangent in the other direction. As long as these 3 points are aligned, you will produce no visible kinks on the surface of the sphere. So here what I'm doing is selecting the whole set of control points that determine somehow the tangency in this kink point. So if I select all this plane of points, I can do whatever I want, including rotation, for example, including scaling like this. Okay. Now scaling is not allowed. Well, rotation also should be performed in a different way, because if I move this, for example, in this direction, well, I can create some kind of nice, smooth, complex surface. This is quite a complex surface, and moreover, if I do this with the opposite plane as well, I can create this, which is some kind of ellipsoid. Okay, but I can also create like an asymmetric stuff like this one. Okay, so this starts to be some kind of complex shape, but you see that I'm only creating it by deforming a sphere. Now, what I cannot do is change the this 3 by 3 structure in the sphere, whatever it be. I mean, it can be this one, it can be this one, whatever plane, whatever face of this curve, I cannot alter this configuration of control points. So if I take this set of control points and move it, there is no problem. But if I rotate them, the rotation, what it does, it produces no particular consequence in this plane, but it is shifting these points from this face of the cube. And so a discontinuity starts to appear along this edge or along this isocurve, and also along this isocurve. Okay, you see that a crease starts to appear. So if you want to deform the shape of the sphere, you must take into account this particular property, which is the faces of the topological cube of this object. And the same happens to this one. Okay, so as this is homomorphic with the sphere, I also have this cube-like structure with more complexity in the profile direction, of course, because it's not a single arc like in the sphere, but I have the same behavior. So if I want to deform this, if I take, for example, only, I don't know, 3 control points, like this, and this, and move them, I will be changing this face of this control solid. Okay, so if I do this, you see I start to create a crease. Okay, but if I also take its neighbors, like all of this thing here, then in this case, I can produce a smooth deformation because I'm not changing anything, because these 3 points are not going away from this face here. Okay, and also, therefore, what I can do is eventually go into the front viewport, select all these belt of control points, and if I select all of them, what I can do is eventually do something like this, and I am changing the topology, the shape, without altering the topological condition of the faces of our control solid. Okay, and therefore there is no visible crease during this deformation. Okay, so the deformability and the topological aspect of a revolved surface depends absolutely on the profile on one hand and on a circle on the other hand, with all the consequences of this particular circumstance. Okay. Now there is another thing that we can do. So, for example, if I draw a circle, okay, like this, see how all the topological considerations that we are performing now on surfaces depends on the same consideration, but on curves. So sometimes it's better to see things from the curve point of view because it is simpler to analyze it, but it's 100% valid for surfaces. Okay, so we know that if I take this is basically a degree 2 curve, a rational curve. It's very easy to create creases or vertices along the path. Okay, but if I take this curve and rebuild it, like a degree 3 curve with, I don't know, 16 control points. Okay, then I get a regular distribution of control point along the path of this line. Okay, and I can use this for whatever I want, basically. So I can take, I don't know, this control point, this one, this one, this one, this one out of 2, basically. And I can do something like, I don't know, this or this or this. And eventually I can rotate this point and create something like this kind of curves, because this is now a totally deformable organic shape. Okay. And I can do these things also going out of the horizontal plane in order to create this kind of very complex curves in 3 dimensions, right? So it's very easy to work with topology once you know the tricks. Okay. Now, I can also do this with the revolved surfaces, and it's very interesting because if I have this limit of the circle rule in the horizontal direction, what I can do is create a revolve with this profile along this axis, and then I can say I want a deformable revolve surface. So if I say deformable, yes, okay, you see that another parameter appears, which is the point count. So if I want to convert the rational circle into an organic degree 3 control point curve, I have this chance to decide how many control points I want. For example, let's say 32. Let's exaggerate. Okay, and I want to create this as a full revolve surface. Now you see that the set of isocurve is already telling us that there is some difference with respect to the original object, right? So we already know that these are knot lines, so we understand that there are lots of knots along this surface in the horizontal direction. If I take this, as this is a closed surface, I can activate its control point and I have access to this complex topology, which means that now any deformation that I want to do will result in an organic deformation and not the creases or kinks or whatever. Okay, so for example, I can take, I don't know, as we were playing with our circle, we can simply reproduce the same situation by taking few control points, not a complex set, because this is going to be quite a long process. I'm just going to concentrate of 3 control points per quadrant, like this, and also like here, 3 control points per quadrant. Okay, so I have this set of points, and now I can do whatever I want with these points, because this is going to result in an organic deformation. Okay, so I can do, I don't know, whatever, basically. Okay, so see how we are creating complex situations here, which would be extremely difficult to create with some direct surface modeling. Where direct surface modeling means, of course, that you create some construction lines and then you start trying with, I don't know, some sweeps or some, who knows, right? But in this case, with topological deformation, it becomes very, very easy to create this kind of objects, okay? So this is the main difference when you create a deformable revolve surface. Now, there is also an in-between, okay? So for example, the problem when I create a deformable surface like this one is that its complexity increases like all over the surface, okay? But I can also create, well, let's say this complexity in a more topologically direct way, okay? So for example, if I want to produce some kind of particular deformation in a glass, okay, so let's try and draw a glass. So in order to draw a glass, eventually I would need also some thickness for this object. So I'm going to front view and offset this thing with a through point, so I can give a very small thickness initially. And then I will take this rectangle and move it so that this vertex is here. Okay? So I need this as a reference set of curves. So now I can take, for example, a NURBS curve. See that I'm not working with, for example, if I wanted to create a profile for a glass, I could also do something like this. For example, in the front viewport, where I see these 2 rectangles, I could also create a Boolean curve like this one, which is this. And then eventually I could also fillet. Let me get rid of the 2 rectangles. And I could also, well, explode this curve because I don't need this side here. So it is open on the bottom. And then join this back together. And then eventually execute a fillet corners with, I don't know, a radius of 1. Oh, why is not filleting this? Eventually, this is weird. It should, but anyway, this is way quicker than any other process that we might want to realize. Oh, I think 1 is too much. Let's see if 0.5. Yeah, 0.5. So I can do this, but we already know that this is not the best solution because I am filleting, which creates some internal discontinuity along the profile. And if I have internal discontinuity on the profile, the moment I create the revolve surface, I will have the same discontinuity along the object. Now, in this case, for example, you see that there is no visible edge, internal edge. So this discontinuity is not a tangent discontinuity, okay, which is the typical situation where you have internal edges appearing, but it is a curvature discontinuity, which is not taken into account during the revolve So you see that we have the absence of internal edges, which means that this is still a closed surface. It's like taking this sphere, for example, and taking, I don't know, all the top part of this object here, taking this point here, and this, select all the U direction and pushing this all the way down to the bottom. And you can create some shape like this one, okay? So this is still a surface, but as we created a profile with this tangency continuity, we could get some discontinuity the moment that we move this set of points, okay? So for example, if I select this and select all the U direction, and I try to do this, you see that I am creating a crease, okay, along this edge. So this is not the best way to do this. That's why I tend to use the NURBS curve in order to create also this simple shape, okay? So in this case, what I'm going to do, I'm going to get rid of all the rest of geometry. So I go into the front viewport and draw a NURBS curve inside this area. Now I'm going to simplify things a little, so I only need a control point before the vertex, another one here, and another one here. And then I'm going to create another one here, another one, and then one here on the left, and then I go down and create another vertex, control point, and finally end in this endpoint, okay? So it's not a perfect profile for a glass because this is not flat in this bottom area, because there are only 3 control points. We should need at least 4 control points in order to have a flat segment for this curve, as we saw with the basic rules for topological design. But I don't care in this moment. So I have a perfectly smooth profile. I'm going to lock all the rest, okay? So I can revolve this object around this axis with a full circle, okay? And so this is totally different. We have a closed surface, but there is no internal discontinuity because we work with a smooth profile, okay? Now, I want to create some kind of engraving or some kind of engraving, a circular engraving at this height of my glass, okay, or some kind of bump on the surface, okay. So what can I do in this case? I can do 2 different things. So let's consider this like the original glass, okay. First thing that I can do is take the original profile and let's also preserve the original profile here, okay. So I always have the original curve, and then take this one, and as I need to create a bulge, for example, here, and I don't have control points, what I need to do is to change the profile topology, okay. So eventually I go here, I start adding, well, in this case, for example, it's irrelevant if I add knots or control points, because the curve is so flat that if I want a set of control points in this area, even if this is a smooth curve, it's probably the best way is to use a insert control point. Also consider that this along this vertical direction we have 4 control points. So basically there is a knot here more or less and a knot here more or less that determine this flat portion of the profile. So in this case, eventually, instead of inserting a knot, I prefer to insert a control point, so I can directly decide where I will place the bulge along this curve. So you see that if I move along this curve, the control point follows more or less, because remember that control points don't lie on the curve, lie on the control polygon. So there is a difference between the control polygon and the line. So I need a control point here, and eventually another one here, and another one here, and another one here. So these 4 control points allow me to create a flat bulge on the surface of this glass. But I also need this flat portion of the line to, let's say, let's do something like this. I am creating this set of 4 control points, so this surface can potentially do something like this. Okay, so be flat in this portion. Okay, But I also want this curve to don't connect directly to the upper part of the glass. I want this to come down and create this kind of situation. Okay, so come down and go back to flat on the side of the glass. So I need more control points, basically. Okay, so if I need more control points, I need them in this area to go flat before reaching the top of the glass. So I will place eventually, you see that I have 2 control points here. So I need another couple of control points in order to maintain this side flat. And so I will take, for example, 1 and 2 here. And then I need also 1 here and another 1. Because at the bottom, I already have other 2. Okay, and that's it. Now I will leave these 2 untouched, and I will select these 4 control points, and I can move it away. So I have this flat bulge, and the curve stays flat before reaching, sorry, I think I took too much, yeah, 5. So yeah, these are the 4 that I need. So I create this flat bulge, and I go flat before reaching the top, and I go flat before reaching the bottom, okay? And of course, I can take the whole set of 8 control points here and scale them vertically if I want to reduce the shape of this bulge. If I do this, I am controlling the topology of the profile before creating the surface. So if I revolve this profile along this axis like full circle, I get the desired result, okay? And there is no problem with that. This is good for creating, let's say, this kind of geometrical variation that flow all around the revolved surface, okay? But this is not good if I want to create some kind of local deformation. So for example, the other alternative that I have is this. Let me further move this, and let me save a copy of this profile. I could also take these points here and move them back. Sorry, move them, well, point and perpendicular to my original ray, okay? And leave them here. Once I have the topological condition, we know that this will be taken into account during the revolve command, because we saw that the revolve maintains the topological complexity of the profile. So if I revolve this thing around this axis, even if it is not deformed, I already have the correct topological conditions for creating this kind of deformation. So I can do this once I have created the revolve. I can go into the front viewport, have access to this set of 1, 2, 3, 4 control points. And I can do exactly the same thing after creating the revolve surface, okay? But what I cannot do with this kind of situation where the profile has already the right topology is create local deformation. Why? Because this is the rule of a circle. So the deformation that I produce on one side will eventually affect the other side of the square eventually, and eventually create creases. Okay, so I cannot use this method for creating local deformation inside the revolved surface. So for example, what I'm saying is that I can eventually do something like this. So a deformation that happens only on one side of the glass without creating any discontinuity, because I'm not breaking the circle rule. But I cannot do this in like, for example, I don't know, I want this thing to be narrower, like this. I cannot do this because now I am creating a crease here. Now, can or cannot do depends on what we want to achieve. Of course, this object is still a valid object, okay? But it's not smooth. So normally we tend to create some deformation that don't break the smoothness of a surface, okay? So that's why I see we cannot do this. But of course you can, but it produces this kind of consequence. So yes, we can get to the same result like with simply a topological adjustment of the profile without editing the shape, okay? But we have this kind of limit. Now, the other thing that we can do, of course, is to avoid creating a customized profile and go back and work with the original profile, okay? So what we can do in this case is, okay, let's execute the revolve surface like with the original profile without any topological editing, but the right structure in order to create this smooth rounding here at the top and at the bottom. Okay, so we get to this surface. Now we know also that we did this with the curves, but we are actually going to do this with the surfaces. Okay. Now, what we can do with this surface is basically get to a more suitable topological condition in order to create local deformation. For example, if I want to create some local deformation in this area, okay, like converting this glass into a jar, like in order to serve water instead of receiving water. So what I'm going to do is I need more control points in this area, right? So I already can do this. Okay, I can already add control points along this surface. If I add, for example, knot lines, and I add knot lines, for example, in the horizontal direction in order to better isolate this upper part of this surface, I would add a knot line on the outside, as well a knot line on the inside of the surface. Okay, like this. And also eventually one other here and one other on the inside. So I get these control points in this area. And I can also invert the direction. So toggle the direction. I go into the profile direction. And eventually I can also activate symmetrical in order to create symmetrical set of knot lines around the area where I want to work. Okay, so I can do something like this, and who knows, eventually this. Okay. So I'm creating this kind of topological variation, but this is still, if I try to rebuild it, this is still a degree 2 surface, okay, in the horizontal direction. So whatever thing I do here, I will always be dealing with some kinks. And eventually the only kink that I see here is this set of points. So if I select the V direction, these are kinks. So if I move them away, you see that this kink becomes more visible because I have more local deformability due to this amount of control points. But if I don't work with this kink, now I have these points available, okay? And these points on the side, if I try to move these points away, you see that they don't produce discontinuity. They are basically smooth control point, okay? So if I don't break the circle rule around the kink line, I can still create some smooth deformation. So for example, if I take this set of points, like starting from here and reaching, on the other hand, correspondent kink point, and leaving the one here at the bottom and the one here at the bottom, okay? So starting from these two kinks here, I'm going to select, for example, all the set of control points here. So if I do this and move this away, you see I'm not creating any crease along this surface because I'm not breaking the circle rule, but the circle rule is now more local because I have added many knot lines and many control points along the way, okay? So you see that the internal edge is deforming smoothly because I'm not working on kink points, or well, yes, I'm working on kink points, but on the profile direction, okay, which is smooth. And it's not producing any kink in the horizontal direction because I have created this structure of control points here on the sides, okay? And I'm not touching this face of the original cube, let's call it so, and this face of the original cube. So everything stays smooth in this case. And I can play with these points as I want, like also creating this, because I'm not changing anything that regards the kink aspect of this surface. And this is also is still more evident if I work with these new control points here. If I work with them, I can do basically whatever I want. So if I select this set of control points and this set of control points here, I can, I don't know, move them apart in order to recover some uniform thickness here and do whatever I want, and still I'm not creating any kink line or any crease along the surface, okay? So we can, if we want some local deformability, we cannot work with the initial topology because we will always miss the correspondent longitudinal necessary topology because this will always be based on the circle rule. okay? But if we want local deformability, you have to make some topological editing after creating the surface, which, by the way, means creating either knot lines or control point lines or kink lines as well, if you want to create some creases along the path, along the surface, okay? And then there is the last. You see that I never recommend rebuilding things as first option, because this is the rebuild is a dramatic operation. Okay, so of course I can take the original surface that comes out from the standard rail flowing along the circle, like copying this, and I can rebuild this surface. Now, of course, in order to maintain this particular shape, which has no creases, it is perfectly smooth, but it has very sharp roundings here at the top, okay? And also we have 90-degree here at the bottom, more or less. So in order to rebuild this, yeah, question. Sub-D solving decision, Jose, sub-D solving these issues with discontinuity, well, this is a big word. I'm going to discuss this in a while. Okay, let me finish this explanation here, and then we will eventually go into sub-D considerations. But anyway, this thing here is actually going to be rebuilt. And you see that as we have these sharp creases here, or sharp rounded corners, I cannot use a small amount of control points. Okay, so remember that U direction is the horizontal circular direction, and V direction is the vertical direction. Okay, so of course I want to switch from degree 2 to degree 3 in the horizontal direction in order to avoid the problems of creases and kink lines along the side surface of this glass. So this increasing the degree, the U degree to 3 is perfect. But I also need, for example, much more control point in the V direction. Okay. So for example, if I stick to 13, I still have a very important deformation like this, because this is going to use 13 control point distributed all over the profile, which starts from here, go here to the right, then to the top, and then goes down in the inner part, and then goes left to the axis. Okay, so these are very few control points because they are evenly distributed along the path. So I need way more than that. Okay, so if I do this, for example, you see that I start to go back to a more controlled situation, but this is still not enough for the upper part of the glass. And so here, for example, if I increase to 100, I should start to have a more precise representation of the upper part, yes, but I still have this kind of bulgy behavior. Okay, so this is something that if you want to recover this kind of situation in a perfect way, you should increase this amount way too much. Okay, so see how we are forced to use a very complex topology in order to rebuild this thing and stay faithful to the original shape. And also, if we see this from the top, okay, like here, you will also see that there is some slight deformation between the original surface and the rebuilt one. So even in this case, I would have to increase the amount of control points to have a better coincidence between the two objects. So we are creating, just so that you know, a surface, a closed surface. It will be also always a closed surface, but with this kind of topology, which still have problems. Okay, so if we go into the front viewport, we will see that there is some weird behavior in this area. Now, for example, this is not so difficult to solve if you want to, I don't know, like recover some vertical direction in the surface, vertical orientation for the surface in this area. But we can do this at the profile level, not at the surface level. So for example, if I activate the control point, you see that I have this kind of weird behavior, but then I have a straight line of control points. So eventually I can take these three here and use the same command that we saw yesterday, which is the set XYZ coordinates. And what I want basically is set the X coordinates of these points to be equal to the X coordinates of this point here. So I am basically creating a straight line of control points. But this is not enough, because actually this line belongs to a very complex surface. So I only took care of these 3 control points, but I still have this one here and this one here and all the rest around these rings of control points. So this is not going to be easy, okay, to regularize this kind of situation, right? So this is why I do not recommend to make a rebuild of this surface. Of course, if you do this, on the other hand, there is some advantage of doing this, because you already have a degree 3 surface that you can edit however you want to create the local deformation, but at what price? Okay, so this is basically the main difference in working with a direct topological approach or with some kind of generic topological approach like the rebuild commands. Okay. Then there are other types. Well, there is another type of Revolve surface, which is, well, actually it's somehow problematic, but it can be useful to create some nice, let's say, complex Revolve surface also from the let's say rotational point of view. So you might know, for example, that there is a right-click command which is rail revolve, where you are allowed to select a not necessarily a circular revolve, but a revolve which is determined by a rail curve. So you will have profile curve, axis curve, and rail curve. And if you, for example, create a rail curve like a polygon with, who knows, maybe 6 sides, like starting from here and with its vertex here, okay? And then we can select, for example, rail revolve, where the profile curve is going to be this one, the rail curve is going to be this one, and the axis is going to be this, and we are getting to this kind of revolve surface. Actually, this is not a surface, this is a polysurface, because our rail has vertices, so visible kinks, okay? And therefore, the object that comes out is a polysurface. But the only topological thing that I want to point out in this case is that if I take this curve and create, for example, a NURBS curve like, well, let me do this with a controlled construction. Like I'm going to create a polar array polar of this object around this thing, like 24 times, like this. Okay, so I need this just as construction reference, so I can create a NURBS curve starting from here, going like to this. Let me turn off the center, like having these control points here. Okay, so I'm using the radial lines only as references to create these control points, to place these control points in a very controlled way. And I'm going to close this line. Okay, so I have this curve, which is a smooth curve, an hexagonal smooth curve, that I'm going to use as the rail. So I have a smooth profile and a smooth curve, like a rail. And then I do rail revolve, profile, rail, and axis, and I get one single closed surface as a result. Okay, so of course the topology depends in this case also on the rail curve, because it is something that it's affecting the shape of the object, right? So same topological consideration right now, but they should involve the rail curve as well. Okay, so I won't go through the same set of observation, of course, but you can already understand what are the tricks in this case, right? So any questions about these methods here before giving a quick opinion about sub-D? Yeah.
Question just to recap, because I understand really well that if you have a degree 3, you can make topological deformation without having any discontinuity.
Yeah.
But if you have a degree lower than that, you start having this kind of discontinuity.
Yes.
I mean, this is what I understood.
Yeah, not necessarily. Consider that in this case we are considering a particular degree 2 continuous curve, which is the circle. And the circle is a particular curve because it has some full multiplicity knots along the path, which are the quadrant. In that case, you have kink points. But if you work, for example, with a degree 2 NURBS curve like this one, and you start placing your control points like here, you still see that the control point don't lie on the curve. So if you take this point here and move it around, you get no kinks along the path, right? So the problem with the circle is that the circle is not a standard degree 2 NURBS curve. Okay, it's a very particular degree 2 NURBS curve. If you want, I can show you this picture that's from the book, because this is really well explained inside the book. So let me take here all the images, and I'm going to find it quickly because, yeah, here it is. Okay, you see it? So this is, for example, the way you create a circle using a NURBS curve PW key. Okay, so you have the control points, which are basically the defining the square structure. And then you have the weight of the control points, that is alternated 1 and square root of 2 by 2. Okay, and then this is the knot vector, which is a full set of, well, a complete set of full multiplicity knots. Okay, so this means that you have 1, 2, 3, 4, 5 knots. Okay, which means you have 4 spans, and these 4 spans are exactly the 4 arcs that you see here, from this knot to the next knot. Okay, and you also see that this, as this is a periodic curve, this full multiplicity knot here actually corresponds to the original, to the initial one, because this curve reaches to the end point corresponding to the starting point. So the 4th knot span leads to the start point again. So it's a very particular curve, this one. And in this case, as this is a degree 2 curve with kinks along the path, because these are full multiplicity internal knots, then whatever type of deformation you do with the control points, you will have some vertex appearing. But this is a very particular case, okay? It's not like a general rule, as you can see here, for example.
Are there other particular geometrical shape
with this behavior?
Maybe not this behavior, but something that is good to know as the circle.
Well, everything that is derived from the circle, like an ellipse curve, for example, it has the same problem. In general, if you think about it, the polyline is another particular case in this sense, in which you have a degree 1 curve, and you have a knot, a set of knots, which are in this case coincident with the control point. Why? Because if you, we saw that in a degree 3 curve, the uniform knot vector contains only a sequence of values that never repeat along the vector, okay? With the exception of the first knot and the last knot, which have full multiplicity, okay? But if you consider a uniform knot vector, you will have, for example, I don't know, like 0, 0, 0, which is the full multiplicity first knot. And then you will have 1, 2, 3, 4, 5, etc., up to the last knot, which repeats 3 times, okay? If you want to create a kink inside a degree 3 curve, you need a full multiplicity knot value inside, in the inner part of the knot vector, okay? If you decrease the degree and you go to a degree 2 curve, you need a full multiplicity knot inside the knot vector, which means that you have one value that repeats twice. Like, for example, 0, 0, and then you have 1, 2, 3, 3, 4, 5, 6, I don't know where it ends, okay? But when you go to a polyline, there is degree 1, okay? So you will have the first knot will be simply 0, because full multiplicity means that it repeats just once, right? And you will have also 1, 2, 3. They are all full multiplicity knots, okay? So in that case, each knot produces a kink, which is a vertex. So in the polyline, these discontinuities here are at the same time, let's say, control point, and they are also knots, and they are kinks, okay? So the polyline is an extremely particular NURBS curve because of this particular situation, okay? But if, as for the rest, there is no particular geometry that by default has this kind of weird behavior. Because if you think about the standard NURBS curves or surfaces that you create with Rhino, like for example, let's do this with a curve, but it's the same if you do it with a surface. Okay, this degree 3 curve, as it has by default a uniform knot vector, it won't have any internal kink. Okay, so by default, you cannot create an internal kink with the Rhino directly. You can add a kink later on, but you cannot create it directly. Okay, you can do this with Grasshopper, but not with Rhino. So it's impossible that you get this kind of strange internal behavior for a NURBS curve that you create like this, or a NURBS surface that you create with any command in direct surface modeling, unless you create it like with a particular set of construction curve, like if you create the Revolve with an hexagonal polyline, then you will have kinks on the sides, on the vertices of the hexagon. But if you smoothen the curve and create it with a degree 3 curve, which by default has no internal kinks, and so no internal discontinuity, be it visible or invisible, then in that case you will get a perfect degree 3 smooth surface. Okay?
Yeah, perfect. Thank you.
Okay, so sub D. Yeah, sub D is a very interesting feature that is going to be added to Rhino. I think that it responds to the need of many users that were used to work with these splines. So it was quite an interesting plugin that suddenly was bought by Autodesk, if I don't remember wrong, and then killed immediately, which is very normal in this world. And then Rhino lost this kind of important plugin that was very popular between Rhino user. And therefore, this sub D suddenly came up with big announcements that were basically not fulfilled in the latest edition. It looks like sub D were going to be included in Rhino 6, but in the end, this goal was basically not achieved. And now it looks like they will be officially in version 7. So sub D is it's a very interesting way of modeling, but at the same time, as it is based more or less on the same principle, it is something that is in between NURBS object, mesh object. It produces some kind of result that I particularly don't like. Okay, so in terms of continuity, yes, if you work with sub D, there is this way of creating subdivision surfaces that are basically, if you think about the NURBS surfaces, is a nonsense. Okay, so when you talk about subdivision surfaces, you are normally talking about meshes. And in that case, for example, there is always this transition between the sub D object and the mesh object and so on. And when you switch, for example, when you switch to NURBS object, then normally you will have polysurfaces with all the consequences of having polysurfaces instead of one single surface. In terms of continuity, yes, it allows to create very smooth set of surfaces or very smooth meshes, actually. So yes, you might say that it solves the continuity problem. But I think that in order to solve the continuity problem, the only thing that is needed is to understand the continuity problem. So once you understand the continuity problem, how to deal with it, how to prepare the topology, and how to, let's say, connect surfaces in the proper way, there is no continuity problem. Sub D makes it easier, and as everything that makes things easier, I don't trust it 100%. So it's like having a plugin. I never use these splines, for example, because plugins simplify some processes. But when you simplify when some processes are simplified, you are not forced to think about it. You just simply go and move things around, and everything looks perfectly smooth, and you don't question yourself on what you're doing. But this is my particular approach. So I'm not saying that sub-D are not useful. On the contrary, but it's not my preferred modeling method eventually. And also, if I want to work with meshes, normally I don't even use Rhino. Eventually, I can use Grasshopper for very particular application. But normally, as you can see here, I work with Blender if I want to work with meshes or subdivision meshes, subdivision surfaces, and so on. Okay. So yeah, it's going to be interesting, but on my personal workflow, it's not going to occupy a relevant place. For example, as regards to these new features that are going to be noted, that are going to be present in Rhino 7, I strongly recommend and prefer the Rhino Insight, for example. That allows Rhino to run as a, well, there is a friend of mine, a dear friend of mine, that calls Rhino 7 the parasite, because actually with Rhino Insight is going to become some additional plugin for several software. And the main one that I'm interested into is Revit architecture. So I work on interoperability between Rhino and Revit since almost 15 years actually. So this is a topic that is absolutely interesting to me. And actually Rhino 7, as you know, is available as a work in progress for those who have a Rhino 6 license. And I invite you to take a look at this feature, because it is very interesting. It's not actually a revolution from my point of view, because I was already working with IFC exporting and importing. So basically, it's the same workflow actually, but it happens in real time. So it's not a like rocket science or an absolute innovation, but it's the workflow is becoming more smooth in this case. So that's an interesting feature from my point of view. Okay. And one last observation. Yes, it's very easy with sub-D to produce some organic design, for example, but on my personal approach, I wouldn't rely on sub-D, for example, for creating extremely controlled surfaces, like, I don't know, automotive design or something like that. Okay, it's very easy to create something that resembles the shape of a car, but I wouldn't use the sub-D to create the shape of a car. Okay, so it's a nice tool for start playing with the subdivision surfaces, but I prefer to work with other tools in that case. Okay, so
So you will recommend Rhino Insight?
Rhino Insight is a very interesting tool, Tiziano. Yes.
Especially for the
interoperability with Revit architecture.
Revit.
Yeah. But as far as I know, it's going to run also as Parasite for other software. But my personal interest is in interoperability with the Revit and architectural workflow. Even if in that case, this is a little off topic, but in that case, for example, there are problems with Revit itself, not with the workflow. So Revit itself has it has a specific way of working and understanding geometry that makes it still impossible for Revit to understand something that might come from Rhino Grasshopper. Okay, so this is already too much for this off topic. Okay, as you can see, also the Revolve surface, which is a very basic command, when you analyze it from the topological point of view, has some tricks that you must consider in order to get to the right result in less time with less effort. Now let's go to the problematic surfaces. Okay, which are the surfaces that I don't recommend using unless you are either at the end of the modeling workflow, so you basically don't need to do any other operation on that surface, or that kind of surface is absolutely the only choice you have for solving this a very precise modeling step. Okay, so either you are at the end of the modeling workflow, or you have no other surface creation method available in that particular situation. Okay, and these two objects are the surface from network of curves and the patch surface. Okay. Now, I see daily, basically, that many Rhino users tend to use the surface from network of curves in order to solve almost any problem or any to create any surface. Okay. Now, I'm going to explain this like this. Okay. So I'm going to take a very simple situation. Okay, which is a rectangle, and I'm going to explode it. Okay. So if I want to create a surface here, well, I can use almost all of these commands here, no? Because I can use the surface from 4 points, and I get this one. I can use the surface from planar curves, and I get this one. I can use the surface from 4 edges, like using only 2 of them, or only 2 of them, or all the 4 edges, okay? And I get this result. It's flipped because of the orientation of the curves, but it doesn't matter. It's absolutely the same geometrical result. I can use, of course, a sweep. So I can sweep along this rail, this section, or I can sweep along this rail, this section, or I can sweep, for example, along this rail, both sections if I want. Okay, so I can create exactly the same result. Of course, sweep 2, so 2 rails and 1 section, and so on. Okay, there are many possibilities with this command because it depends on which rail and which curve you are selecting. And then there are these complex things, like, for example, the surface from network of curves. So you select the curves, and you get this. So we already see a different topology, right? And then there is this other one, which is the patch between these curves, and we get this, which is a totally different thing that we are getting, okay? So now, you see that it's evident that there is a difference between all these commands, right? But you also see that all the first commands that we have used produce more or less the same result, okay? Besides the orientation of the surface, that depends on the orientation of the curve, but the geometry and the topology are identical, okay? But if you use, for example, the surface from network of curve with these very simple lines configuration, you already get this thing here. And this thing here, despite the fact that you are using 4 edges which are straight and linear, okay, you get a surface which has this kind of topology. And with this kind of topology, for example, you also see that if you take these points and move it up, you have a degree 3 surface in both directions of the rectangle. Okay, so U and B are degree 3 directions, with a set of 1, 2, 3, 4, 5, 6 by 6 control points. Now, why? The reason why is that the surface from network or curve doesn't work like any other surface creation method. Okay, it works by using the construction curve with a tolerance. Okay, normally the edge curves have a tolerance which corresponds to the absolute tolerance of the document, because Rhino says that probably this surface is going to be, let's say, adjacent to another surface. So you eventually want this surface to stay in contact with the neighbor. And if you use this kind of tolerance, then the surface will be touching the correspondent edge with enough level of precision, so Rhino will consider that this surface and the adjacent one are touching each other along the edge. That's why edge curves are taken into account with this very precise tolerance value. Okay. While as for the interior curves, the value is smaller. Well, in absolute terms, is smaller, because so the tolerance is more, let's say, generous. Okay, so this surface actually would pass through interior curves with let's say less precision. Okay, so everything is based on these two values here, right? So if you work with a surface from curve network, the network of curves that you are creating is just taken into account as reference and not as precise cross-section or precise internal curves, okay? So this has many consequences, okay? Because if you work with just the four outer edges, you have no problem, basically, because who cares, right? The only thing that I need is that the surface touches the edges using the document tolerance. And then what happens next, it doesn't matter. But what happens if I have complex edges? So what happens if I take, for example, a complex edge, which means eventually something like this. It's already complex. And eventually something like this, and something like this, and this. So if I do a network surface here, sorry, a network surface here, I start to get this. Why? Why this amount of isocurves and knots, and therefore the control points? Because I am basically performing an operation which is like rebuilding all these four edges here using this tolerance, this fitting tolerance. Okay? And therefore, you have a very, very complex set of isocurves and internal topology that make this object basically more difficult to use in any further or either modeling or topological editing, whatever you might want to do on this surface here becomes extremely difficult to perform because of this very complex topology. Okay, so my message, my general message as regards the surface from network of curves, don't use it unless you got to the final stage of your modeling workflow, because it produced this kind of extremely complex result. Okay, and the fitting tolerance as regards the edges is by default the absolute tolerance. But if I want if I can be more permissive, for example, along the edges, and if I let's say work with a more generous tolerance like this, you see that the surface comes out way more simple than the original one. But on the other hand, I start to get this kind of behavior here, where the surface don't take into account the edges too seriously. Okay, so starts to have some interesting deviation or important deviation. Which degree will have this complex surface? Well, this has 3 by 3. There is no possibility of controlling the degree. So as all other geometries in Rhino, where you cannot control the degree, it will have a degree 3. Don't think about the blend surface in this case, because this is not a single span surface. Okay, so you see that if you do this, for example, these isocurves are not, let's say, visual isocurves. These are knot lines. And as knot lines, it means that this is a knot span, another knot span, another knot span. So as this is not a single span curve surface, then there is no increase, automatic increase in the degree. Okay. So if I go into the details, you say that U is degree 3 and B is degree 3. Okay. The only surface that automatically gets a degree from the number of control points is the blend surface. Okay. But in this case, this is more than enough to rethink using the network surface for creating actually usable results. Okay, so, and there is also the interior curves. Now, the interior curves, for example, means that another problem with working with a network of curves is this one. So if I want, for example, to create some controlled deformation inside this surface, like a bulge, for example, in this corner. Of course, I can take this object here, create the surface with the desired tolerance, eventually like a very high tolerance, and obtain this object here. Eventually, I'm going to analyze this in order to bring the internal parametric coordinate system to the right orientation. So I'm going to flip the vertical direction. And as you can see, red should be pointing to the right and green should be pointing to like up. So I have to swap U and B in this case. And now I have the correct internal coordinate system, and I hit enter. Okay, so I have reoriented the surface in order to have the proper orientation. And now what I can do with this, in order to create a bulge in this area, the more efficient way is to use the soft move command, because take a look at how many control points we have here. the topology is so dense that the control points start to be coincident with the knot lines, okay? Because they are evenly distributed, there is a uniform knot vector, so there is this apparent correspondence, okay? So take a look that the control points never lie on a knot, on a knot line, or isocurve, as you might want to call it, okay? They are always on the outside of the curves, because there is no internal discontinuity, no kink in this case. So the more convenient things that we can do is create a soft move command like this, select the area that we want to consider for this deformation, for this bulge creation, and eventually select a center area and say, okay, all the points that are inside this area are going to raise up like this. This is the only thing that you can do realistically on these surfaces, because the topology is so complex that it's basically impossible to move or to edit the control points one by one in order to get some smooth variation on the surface. Okay, so you have to use some control deformation, control transformation, like the smooth, the soft move, in order to create this kind of result. On the other hand, if I want to create a bulge in this area and also play around with this bulge, what I can do is, so this is an alternative, right? This is one solution. But I would solve this problem in a different way. Like, for example, if I want a surface which is more or less flat, okay, but I want it to be topologically editable, I cannot use, for example, a surface from planar curves, because the surface from planar curves create a rectangular surface which is trimmed using the outline that we have selected as planar curves. So this is a trimmed surface, but this is a rectangular surface. So if I activate the control point, I see that the actual surface reaches this outline here, which is the rectangle. And then this rectangular surface is being trimmed with this silhouette here. Now, being this a rectangular, a trimmed surface, it means that its topology does not correspond to exactly the boundary of the surface that I see. Okay, so trimmed surfaces are like let's say a visual operation where you see the final result, but the topology stays untouched, right? So being this a rectangular surface, it means that it has no deformation possibility on the inside, because there are no internal control points. Okay, so if I want to do something with this surface, I should rebuild it, give the surface degree 3 in the both direction, and have control points in this area. Okay. But if I do this, for example, in this case, from a topological point of view, if I do this also with, I don't know, 16 by 16 control points, okay, like this, you see that I am changing the topology of the rectangle. And this is a problem, because if I want to produce some kind of deformation in this area, and I, by chance, I touch, for example, these points that are very close to the edge and do this, my surface is going to deform along the edges, and I don't want this. This is the consequence of not controlling the topology along the edges of the surface. So I would never use a surface from planar curve, because I need the topology of the resulting surface to, normally I say this like the surface is in touch with its edges, okay? The surface from planar curve is not in touch with its edges. It uses them to trim the unnecessary part, but it's not in touch. Okay, so what I would use in this case is eventually a very simple command like the surface from 4 edges, like 1, 2, 3, and 4, and I get this one eventually reoriented in order to have the proper orientation, like flip the axis, and once again, for example, if I want the axis to be to the right, the y-axis, the v-axis is already in place, so I simply reverse the u, okay, and hit enter. We already have a proper orientation for the surface. The difference is that you can see that the isocurves is follow the shape of the edges, and basically produce this kind of nice internal movement, which says that the surface is in touch with its edges. So in this case, for example, I already have a degree 3 surface, because I have degree 3 edges on both sides of the U orientation and of the V orientation. And therefore, I can simply add, let's say, control point lines, because this is a flat surface. So I need control points, for example, in this area, in this direction. and also toggle in the opposite direction in order to have more concentration and be able of deforming this surface locally. Okay. Oh, by the way, the control point do not affect the inner part in this case, but yes, they do affect the shape of the surface along the edges, because the topology of the surface is totally correspondent to the topology of the edges. So that's why we got this deformation. If I use insert not, of course, this is not going to happen. So I do this. You see that the surface stays basically identical to the original one. Oh, I was using symmetrical. I don't need symmetrical in this case. So I'm going to add some knot line here, toggle, some knot line here, and I have the necessary control point structure. And if I want to create a bulge, more or less like this one, what do I have to do? Well, we know from the topological rule of curve design that if we align 3 control points in a row, then we make the curve reach this tangent direction. Okay, and if the 3 control points are basically evenly distributed with a constant separation, then the curve passes exactly through the midpoint because it becomes coincident with the correspondent knot. Okay, the same happens with surfaces. Now, if I want this point to reach a specific height, I cannot move only that point because this is a magnet. Okay, this pulls the surface, but not exactly to its position. Eventually, if we want to play around with this, you can change the weight and make this point heavier. So the surface is going to do something like this. But this is a very, very particular situation, okay? And remember also that if you export this thing, you are creating a rational surface, which is not always understandable by other software, okay? So if I do this and I want the surface to reach that height, I must also take into account the adjacent point, okay? So for example, if I take these two here and I move them all up, you see that I create this kind of situation here where the surface is still pulled up but doesn't reach this height. Why? Because the surface is a bidimensional domain. It not only works in one direction, it works in 2 directions at the same time. So in order to get to that height, I also need to consider this and this. And not only this and this, because I am not considering exactly the whole set of points. As you can see, you get this kind of nice cross here, but the surface doesn't reach exactly that height because I still miss these corner points. Okay? So in order to produce a controlled deformation on the surface by reaching a specific height, so being tangent to a plane, for example, and passing to a specific point, then you must select a set of 3 by 3 control points. And in this case, you will see that the surface becomes tangent to this plane and reaches exactly that height. Okay? So this is important because using the same topological rules that we saw with curves, we can work with surfaces. So let's say that we want a flat area, a flat bulge in this area. We must also take into account moving this set of points and this set of points. So 4 by 4 control points will produce a flat area in the knot span that corresponds to the inner part of this region. So if I move everything up here, there will be a flat area more or less in this part here. Okay, so you see that we are creating this kind of nice bulge that we can control. We can control in several ways, because if I go back to this and deselect this point and this point, and I take this 3 by 3 set of points, I know that I can reach this height. If I don't want this flat-ish behavior, I can scale this set of points down, you see, and I can create this more concentrated bulge. Or I can eventually, on the opposite, I can do something like this and create this kind of like button style relief on this surface. But I can also play around with this like in a more extreme situation, like for example, increasing them up and then rotating this plane and creating this kind of particular bulge. Like if I work with topology, and I have a direct access to topology, I can do several things, okay? Because all the rules are still valid in this case. Okay, so you see that also in this case, this is an extremely complex situation in terms of geometric aspect, that it's very unlikely that you can get it from any direct surface modeling tool. Okay, so once again, simple command, very simple command like for edge curved surface and topological editing in order to get the proper result. Okay, so in this case, for example, I would never work with a surface from a network of curves. And you might think, okay, so without considering this extreme situation, okay, where I made this extreme edit, but if I try to create a bulge in this area with this command, with the surface from network curve, what I would need? Well, what I would need is internal curves. Okay, because internal curves are basically, they become internal knot lines for our surface. So the surface is forced to pass through the internal curves. So I need a curve or a set of curves that starts from one edge, do something, and reach the other edge, because this is a NURBS surface, not a T-spline. Okay, so I need another curve here and ending like this. Now this is not enough, because if I do this, my surface as a reference in the two parametric direction, in the U direction, it will have this curve, this one, and this one. Okay, and in the V direction, it will have this, this, and this. So if I increase the height of this curve in this area, the surface will start from here and tend to reach the height of this section. So this is not enough. But anyway, let's consider like this is enough. Okay, what's the problem in this case? Well, if you take a look at any of the NURBS surfaces that we have created, all the isocurves always intersect along the surface and lie on the surface. So if I want to create a bulge here, I must take one curve, take its control point, and move them up at the desired height. Okay, and if I want to do this, I also need to take this isocurve, the opposite isocurve, and make it intersect with this U isocurve. Now, in order to do this, I need to prepare the isocurves properly. So, for example, I would need the simplest topology that I need in this case would be one control point on one edge, another control point to determine the initial tangency. Okay, then I want this region of the surface to stay flat. So I need another two control points. So the surface will stay flat in the inner part of this set, right? And then I need three control points to reach to a specific height. And then I need another two control points like end tangent and end point. So a total of 4 plus 3 plus 2, so 9 control points, okay? On the other hand, I need the same for the other curve. So I will need 1, 2, 3, 4, and then 1, 2, and 3 points, and then 1 and 2, okay? Now, with this topology, I am able to start doing something, okay? Now, even if these 4 control points are not aligned, the knots will force the curve to stay on the floor, even maintaining this kind of curvature here. And even if I take these 3 control points here, and they are not aligned in the horizontal plane, they are aligned vertically, so in the Z coordinate. So if I move them up and I go into the front viewport, I will see that my curve reaches that height. Even if the 3 points are not aligned in the X and Y coordinates, they are aligned in the Z coordinate. But I don't want to do this, because as I need to intersect this line exactly in one point, I need this curve to pass precisely in the inner point. So I need to take one line, for example, from this to this point, and place this control point exactly in the midpoint. If I don't do this, it won't be possible for me to consider a physical intersection between these two isocurves, okay? So once I have this structure, I can take this line, rotate it like 90 degrees, and use it as a reference in order to place these 3 control points here. So I can take these 3 points, move them so that this point here is coincident with this intersection, and then take this point here and move it to the end, and take this point and move it to the end point. Okay, so now we have a perfect intersection between these two isocurves. And as we have access to the topology, we can activate the control point, we have this cross of points here, which we don't need the diagonal, let's say so, because this is not a surface. It's not a two-dimensional domain. These are two unidimensional domains, okay? So I only need 3 points and 3 points. And I can decide this bulge, how rounded or how smooth or how squarish it is, okay? On the other hand, I have this flat area because of the 4 control point, and final tangency and final tangency, okay? So this is a set of internal curves that I need, okay? Let's see what happens if we try to create a surface from network of curve. So you see that the command normally tends to auto-sort the curves, because the way that this command works, it sorts all the U curves and all the V curves. Now, in this case, the situation is very clear, because it's clear that we have horizontal lines and vertical lines. But when you try to apply the network surface to a very complex set of curves, you might want to perform this operation. First, select all the curves in one direction, and then all the curves in the other direction. Even if you don't have to press enter during this selection, okay? The fact that you are sorting the selection curves then makes it easier for the command to understand what orientation do the two sets of curves have. And then hit enter. And we have this result. Of course, we are creating a bulge because the surface passes through these isocurves, okay, with this tolerance. If I need less tolerance in this case, I need just like a, I don't know, something like an idea of bulge and not a precise height. I can also use a more permissive tolerance like this. And in this case, for example, you might notice that the surface starts to move away from the interior edges. But normally, if you want to reach a very, very precise height, this should also be a very high tolerance value, okay? But anyway, normally this is set to 0.01 because normally there is enough precision with this tolerance here. The problem in this case is another one. If I confirm this execution here and hide all the rest, you see that the interpolation of this surface starts to create something like this. Now, this is something that you simply cannot avoid using a surface from network of curve. It's basically something that depends on the way that the surface takes into account a complex set of cross sections in both directions at the same time. So what does this mean? This means that even if in one direction you would have something like this, you see that curves never goes through the XY plane on the negative Z portion, okay? This never happens. So why this surface is falling down? It is falling down because it is also doing a sweep in the other direction. And in the other direction, you have a curve, which is this one, which has this kind of curvature here. And this kind of curve, imagine like if this was a sweep to rail, okay, between these two portions of longitudinal isocurve. If you imagine this portion of cross section flowing along these two rails, it will produce this kind of depression here. So that's why you get this thing here, because the surface from network curve is a double interpolation in the U and V direction. So there is no possibility of controlling these internal areas here. You might try, for example, something extreme, like creating additional sets of internal curves in order to flatten, for example, this area. And actually, this might sound like a good solution, but it is not. It will only concentrate the problem in very narrow areas, but the problem will still be there. And there is also another problem. You can think about doing this process, basically, only with few lines, because what we did to create this intersection must be repeated in order to create any additional set of internal curves, which means if I have to add another line here, I will need 1, 2, 3, 4, and then 1, 2, and 3 points, and then 1 and 2, okay? But now, if I need a longitudinal isocurve, I would need 1, 2, 3, 4 points, then 3 points to assure the intersection with this cross section, and then If I am still in a flat area, for example, or I want this area still to be flat, I would need another 1, 2, 3, 4 points, and then 3 for the intersection, and finally 2 for the tangency if I don't want another flat area here. And then finally tangency. Imagine what happens if I start to add another set of isocurves. So it becomes extremely difficult to control these internal edges, internal curves, because you need a very complex topology. And when you have a very complex topology, on the other hand, it becomes impossible to create a smooth deformation for these lines, because you should place the control point in a very, very specific distribution in order to avoid some, let's say, sudden deviation of the curve along the path, which would result in a not so smooth aspect. Okay, so it's very difficult that you can solve this problem simply by adding internal isocurves. Okay, and also if I do this, like use this curve to say that your surface must remain flat all around this area, and try to use this curve for a network surface, you see that I get to a result. Okay, so everything looks like better, but if I go here, you still see I have some kind of weird behavior that it also, in this case, it is also increasing the height of the surface and then falling down and then reaching up. Okay, so this problem is not going to be solved, never, with this method, with this approach. So you see that the surface from network curve is extremely complex to control. And it needs a very specific set of construction curves to obtain a controlled or predictable result. Okay. But in general, if you want to work with an extremely controlled situation like this one, well, this is not the best solution. Okay, I would work with direct topological modeling. Okay, so let me think. Oh yeah, and then there is another thing about this type of surfaces, which is related with continuity, because of course this is the other topological thing which is important. Okay, so as regards continuity, well, let me finish first. Before discussing continuity, I want to finish with this with the patch comment. So yeah, and then we will switch to continuity consideration, going through also the sweeps. Sorry, the sweep to rails, which is also important. So what I'm going to do right now, I'm going to take the edges of this surface, like all of them, and copy them here. Okay, so we have 4 edges here. Now what happens if I create this surface using a patch command? Patch command does something like this. Remember the surface from planar curves, which does something like this? It's evident that there is some analogy between these two surfaces, right? So this looks like this one, but with a more complex topology, right? So what the patch does is quite a complex process. The patch is a very particular surface because it's the only surface that when you execute the command asks for curves, points, point clouds, and meshes. Okay, so it can work with basically any input. Why? Because actually it doesn't use any of these inputs. It creates its own inputs. Okay? How? By fitting a surface through this object. So these curves, points, point clouds, and meshes are only like a general orientation for the patch to work, but they are not input object, real input object. Okay, so the real input object, the real input geometry that the patch will use is created starting from these things that you can select by distributing points along this object and fitting a surface through that point. Now, what does it mean? It means that if you take these lines here and say enter, Then the patch starts doing something like this. It takes these curves, start distributing points along this object here, and then create one thing which is called the fit plane through points. Okay, so imagine that we take these curves here, okay, and use a divide curve by number of segments, like in order to create a regular division set along this line. Like, for example, 10 division for each line. So we get these sets of points, right? So if I take these points here, like this, I have a point cloud, basically, okay? And if I create a fit plane through points, I get this object, okay? Once I get this object, the patch, what it does is rebuild this plane, like rebuild it with a 3 by 3 degree in order to have it organically deformable, and with this amount of control points, which determine this span count. So if I want, for example, to obtain 10 by 10 spans, it means that the surface will have 13 by 13 control points. Okay, so this is the fitting plane with a rebuild that the patch command is creating. And then if the patch detects that all these points here are not at the same height, it starts to take the control point of the surface and displace that control point in order to have the surface fitting, or I mean passing more or less through the points derived by the input object. So this is what the patch does during the command execution. And that's why when you execute the patch, you will see that you have sample points, which basically determines the, let's call it the resolution of the points generation along the input object. And then there is the surface U spans and V spans, which are exactly the knot spans in the rebuilt fitting plane. Okay. And then there is stiffness, which is another width parameter for a surface that basically affects how much the span, the patch, sorry, can displace the control point deriving by this span's division in order to get to the original position of the sample points. Okay, so it's a very complex operation. It's not like, well, taking a surface and deriving the surface from the input object. It's not like that. Actually, the patch is the less precise command when you create a surface. Okay, so what we can do realistically with this, for example, just taking into account this situation here, right? What we can do, for example, is create an internal set of isocurve like this, take the internal point, increase them, their height like this, eventually scale them in order to have a more concentrated bulge area, and I'm going to scale them like this also, so I have aligned more or less these 3 points, and I have more control in this bulge. I can also add a knot along this line, like more or less here, in order to have an additional control point, and I can set point and change the Z coordinate in order to flatten this to the ground and move it around like this in order to concentrate this bulge a little more, and even in this direction. So you see that I am using only topological modeling in this case, just to resemble all the things that we have done so far. And then I need another isocurve, like for example here, flat area, 1, 2, 3 control points, and final tangent. Okay, and then I have this 3 point, and I will take them and move them so that the center point is coincident with this one. Now, I don't care too much about the regularity of this set of points here, because the patch is not going to be that precise. Okay, so I only need to tweak geometry a little in order to control more or less the situation here. Now, in this case, if I take this object and create a division, for example, they are all lines, so divide curve is enough for creating this kind of point set. Okay, now I get these points. Okay, and if I select all these points here, well, now things are different than the previous situation, because this is not a flat point cloud. This is a 3-dimensional point cloud. So when I use the fit plane, I start to get a surface that doesn't respect this point cloud. Okay, and then if I take this and rebuild it with a 10 by 10 number of spans and 3 by 3 degree, I get 13 control points. Okay, and once I have these control points, what the command will do is start taking the control point and move them so that the surface start to pass more or less through this three-dimensional point cloud. Okay, so this is what will happen during the patch command. Let's see it on duty. So let's patch all of this and let's hit preview. Okay, so you see that the surface tends to pass through the input. Okay, if I confirm the command and take this surface and actually activate the control point, you see that I am getting a trimmed surface. So as I was saying, we already saw the analogy between the patch and the surface from planar curve. You can think about the patch as a surface from curves, not being planar. So the patch can create a rectangular topology using whatever type of input you want, because it is only taking a rectangular plane, deformable rectangular plane, with the desired amount of spans that if you go here and see, you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spans in the region of the surface, and then more because it needs more extension for our surface. Okay, so you don't even control exactly the number of spans. The number of spans is the number of spans that you want for the desired surface, not for the whole surface. Okay, so you see that you control nothing about the surface in the end. But in general, this is a rectangular surface, deformable rectangular surface, that is deformed according to the input geometry that you select, and then it is trimmed using the outer border that you have selected. If you select an outer border which is closed, because if you don't select an outer border which is closed, like in this case, the patch will only create this rectangular surface with the deformation, the whole deformation that you can see here with this network of control points. Okay, so for example, if I do something like this, which is I'm doing on purpose, okay, and hit patch, the patch will still create a surface, but it will present all the extension of the surface because it cannot be trimmed with an outline. Okay, so let's consider the patch once again, the patch execution. I hit preview in order to see things from the geometrical result. So sample point 1. This affects the quality of the representation of the surface, of the patch surface, as well as the number of spans. If I create a surface with more spans, like this, and hit preview, this surface would be more capable of deforming in order to reach the position of the input geometry. Okay. Then there is stiffness. If I say that this surface is more stiff, like for example 10, the deformability of the surface, the local deformability of the surface is going to be reduced in order to create a more smooth result. But this will also affect the way that the patch can reach out for the input geometry. Okay. On the contrary, if I make this surface more elastic, then the deformation can become, let's say, uncontrolled, because it's like having a sheet. Okay, so if you use a silk sheet, then this can deform like in a more detailed way. But if you take an iron sheet, then in that case, eventually you have very small deformation possible. Okay, so normally this is set to 1, which is also another parameter that is simply a scalar value. There is no basically way of defining, well, is 1 stiff enough or not? Okay, so it depends on the combination of all these params here. Sample points, if you select 10 sample points, you will have a more precise point cloud starting from the origin, from the original input. That if you have the correct amount of spans, eventually will result in a more precise correspondence between the surface and the input geometry. But as you can see, there is no possibility of controlling directly this object. The thing that is interesting is that this patch here is basically a flat rectangular surface, which was rebuilt, so with a deformable topology, and then it's being the control points are being pulled in order to get to a specific position, which is something that we were doing exactly like here. We took a simple geometry with the right topology, and then created the topological variation by a denser representation of control points in order to create this deformation by pooling the control points. So the patch is similar to a direct topological modeling, but it's not under control because the density of the control point network and the topology is determined automatically by this deformable rectangular surface, and the deformability is determined by the number of spans, and the actual deformation is determined by the patch automatically. Okay, so we have no control over it, but we avoid this curvature problem that we had with the network surface, because the patch doesn't need to make any interpolation between cross sections, because it doesn't work like this. It just takes the input curve and displaces the control points only in the areas where it needs to displace the control points. So there is no, let's say, counter curvature in these areas. Okay. So in this case, for example, it is more useful than the network surface. Okay. And then there is automatic trim. If you activate automatic trim, then the surface is trimmed using the outer boundary. If you don't activate this, then you get the full extension of the surface according to the topology of the plane that has been created and deformed. Okay, but normally you want to keep this activated. For now, let's take a break right now. So the usual 15 to 20 minutes break, and we will finish this patch discussion here, and then we will go into some let's say topology-based modeling, which is also very important. Okay, so I will leave this here as a memory of what we were doing. Just let me adjust the orientation, like flipping and reversing the U, and that's it.